Okay, so in a previous clip, we looked at a very brief, generic overview of acids and alkalis, and we named two acids, one which was HCl, or hydrochloric acid, and the other one which was ethanoic acid, CH3COOH. And we labeled them as essentially a strong acid, which was the HCl example, and a weak acid, which was the ethanoic acid example. And while we were looking at that, we didn't go into any more detail over it, but what we did suggest was that in both of these examples, it's the presence of the hydrogen in both of those molecules which gives rise to each of these substances being acidic. And so how do they act as acids? Well, in order to act as an acid, those substances must be able to donate those H plus ions to another substance. So this H plus ion must react with something else, and in doing so, it defines HCl or ethanoic acid as an acid by donation of this hydrogen ion, this proton, to a substance. So if the H plus ion can be donated, it is defined as an acid in a very simplistic sense. So this is a proton or H plus ion, and so if this is able to donate this proton, then HCl, hydrochloric, can be regarded as acidic because it is acting as a proton donor. Now, ethanoic acid is an acid. It must also, on a basic level, do exactly the same thing. Now, it produces a different counterion, which then goes towards discussing later on what type of salt we get, because as we will label these later, these are essentially spectator ions, and so they get involved in preparing the salt, but ultimately not involved in neutralization of the acid. But what then defines what we now know is HCl being a strong acid, and what we've known for a number of years is that ethanoic acid is a weaker acid because of its simplistic addition to universal indicator, whereby ethanoic acid would tend to give you a yellow or an orange colour, HCl will give you a red colour, it's got pH 1 to 3, ethanoic acid typically 4 to 6-ish, dependent upon its concentration. But what on a chemical level defines whether it's strong or weak, and it's to do with the number of hydrogen ions which are donated when that substance goes into solution. And if you imagine, for argument's sake, we put in 1,000 molecules of HCl, then we have to ask ourselves how many of those 1,000 molecules or million molecules or whatever number we have, how many of those will dissociate, which is the thing we're looking at. It's called dissociation. How many of those molecules will dissociate to produce hydrogen ions? And the answer is all of them. We have what's called complete dissociation, i.e., every single HCl molecule which goes into water when it is dissolved completely dissociates, and every single one of them generates an H plus ion which is able to react. Compare that to the ethanoic acid case, and we don't get complete dissociation. We get what's called partial dissociation. And for every million molecules that go into solution, actually a very small number of them donate initially their hydrogen ions. We get a much lower concentration of hydrogen ions. And as we'll look at numerically, a lower concentration of hydrogen ions in solution leads ultimately to a lower pH and what we regard as a weaker acid than HCl, because we've got this dissociation effect, and partial dissociation would ultimately be regarded in a complete discussion as an equilibrium, whereby we're having partial dissociation of the ethanoic acid compared to complete dissociation